In the following demonstration, we'll analyze the structural performance of an engine mount bracket from Creo in Simcenter 3D. We need to ensure that the maximum deflection of the bracket does not exceed 20 thousandths of an inch when it's under its operating load. We'll begin in Creo by exporting a JT file, which will then open in Simcenter 3D. Now this file is fully associative, so that if there are any changes that occur in Creo, those will be reflected in Simcenter 3D. And we won't need to start over from scratch defining our simulation model. So here to begin, we'll create our simulation models in Simcenter 3D. And we'll also create a linear static solution. Now we'll begin by modifying the geometry that came from Creo to remove features that we don't need. So here, if we take a look at some of the holes, you'll see the faces are divided. Let's go ahead and clean that up. And also here you can see there's a tab on the top of the part that is not important for our structural performance, which we can remove as well. So now that we've prepared our geometry for simulation, we'll go and create our simulation model. We'll create a mesh on the part. And we'll also assign a material. It's made out of 310 stainless. Then we'll define our constraints and our load. We'll fix this face, and we'll put a 1,000 pound bearing load on this hole. Now that our structural model is completely defined, we'll go ahead and solve the model. I'll pause the movie while it's running. Here you can see it took 17 seconds to run. And we can view the displacement results. And our design requirement is to not exceed 20 thousandths of an inch displacement. Here you can see we have almost 27 thousandths. Here we can animate an exaggerated deformed view. And we can also take a look at the stress results to see where we could add material that will have the greatest effect on the stiffness of the bracket. So here where you see the higher stresses are areas where if we add material, we'll be adding that material most efficiently in terms of its effect on the stiffness of the bracket and lowering the overall displacement. So let's go to Creo and make those modifications. Here we'll begin by changing the size of the holes to accommodate a larger bolt. And we'll also remove some of the pockets in order to add stiffness to the bracket. So you can see we've removed the pocket on both sides. There were two on the bottom and one on the top there. Now that we've made those modifications, we'll go ahead and export a second JT file, which then will open or replace the original JT file with the alt bracket 3. So to do that, I'll simply rename the original to -old and the new one to the original name, and then reopen it. And what will happen is you'll see an associative update. Here you can see those pockets have been removed, and also the tab that we had removed earlier has also remained removed. Next we'll go to our mesh. Here you can see the geometry is updated, but our mesh has not. We just hit the update FE model button and our pockets are now gone, and our holes are larger to accommodate the larger bolts. So at this point we're ready to solve our model, because you can see that the loads and constraints also have survived that change from Creo. But we'll go ahead and clone that solution so we can keep our original results and compare them side by side. So here we'll get a top and bottom view. We'll put the original results in the top and our updated results in the bottom. We'll synchronize the views, and we'll also turn off the mesh so it's a little easier to see our results. All right, and then also you can see that we've now met our design criteria of being less than 20 thousandths of an inch total displacement. And that concludes the demonstration.